As promised, now we want to take a quick look and give some intuitive arguments of what happens if you go to two or more loops in the perturbative expansion and you are in a renormalizable or super renormalizable theory, right? For that we use again our poster boy, which is lambda phi 4 at 4 dimensions, right? So when you go to higher loops, there's always this chance that even when the superficial divergence of the whole diagram is smaller than 0, right, there can be sub-diagrams that are divergent, right? So let's see an example of that in the case of lambda phi 4. Right? We have seen that for lambda phi 4, delta 4 is 0, and that means the superficial divergence depends only on the external number of legs, and it goes like 4 minus n. So let's look at a diagram that contributes to gamma 6. Right? So this is not the whole gamma 6, but is one contribution to it. Right? Let me draw it. This is the diagram I have in mind. I can only put phi 4 interactions here, right? And I want to start with 2 lines and finish with 4. Right? And this is the diagram. So I put a loop here, another one here, and this is it. Right? If you want to check if this is possible, just make sure that every vertex has 4 lines coming out of it. Right? So this diagram, since the superficial divergence only depends on the number of external legs, right? This has 6 legs, so D is minus 2, right? So from the superficial divergence criteria, right, this is convergent. But we know that this guy right here, right, we calculated it before, and this guy is actually divergent, right? This is exactly the contribution we calculated for the 4-point function. And this guy diverges by the log of lambda, right? So that's a specific case where a sub-diagram diverges, right? But this is a simple one, because if you think about it, there's no cross terms between what's happening in this loop and what's happening in the rest of the diagram, right? In this case, the divergence is, you could think of this in this way. If I remove this guy, right? Suppose I just chop this divergence off. The diagram will now look like this, right? These will be connected straight to these lines, right? And this is convergent. This is really the minus 2, right? This converges. And there's no sub-diagrams diverging. The fact is that whatever happens in this loop, right? Whatever momentum goes in, right? The sum of these 2 lines here, let's call it P, right? Whatever momentum P goes in here, it goes out through this point, whatever happens with the momenta running through the loop and diverging. And this receives exactly the same momentum. So there's no interaction between these 2 loops, right? If this converges and that one diverges, there will be just a multiplicative factor, which is this log of lambda, right? And that suggests that this is very easy to remove, because we know you add a counter term that conceals the divergence in this one. This is just that counter term that we called delta lambda, is the counter term to the 4-point function, right? And this will be also multiplying the rest of this diagram, which is finite, and there will be a cancellation between these 2, so this sum will be finite. And the important point here is that no new renormalization conditions will be needed, because the expression showing up here is exactly the same we had in the 4-point function. So this guy will have the form when you implement the renormalization condition for gamma 4, right? You already saying this guy is minus the divergent part of this guy, so that is guaranteed by the previous renormalization condition. Of course, life is not always that good. So let's see another example, right? Sometimes what can happen, so again, we're trying to stick to lambda phi 4 here, but there are many theories where this kind of thing shows up, right? Then you can have more involved diagrams. Take this one. Now, this is already a 4-point function. Now it's a contribution to the 4-point function. So we know the superficial divergence is, in this case, 0. So this is a divergent diagram, right? But we want to know if there's a new divergence showing up here, right? Another example is this one. Just the setting sun diagram for lambda phi 4, right? It's the 2-loop contribution to gamma 2, right? The self-energy, and this is the 2-loop contribution to the 4-point function. Now, these are more complicated, because if you look at the momenta going around here, you have K1 here. Let's call the momenta going through the second loop K2 in this case, right? So you have K2 here. I'm ignoring the external momenta for now. Of course, it needs to flow here somewhere, and you have some freedom of choice on how you distribute it in these internal lines. But the main point I want to call attention to is that in this line, you have both these loop momenta going through, right? And that means that when you go to really high K1 and really high K2, right? I have to worry what happens when K1 is big, K2 is small, K2 is big and K1 small, and when both of them are big. All of these are limits of my integration in the loops, right? Same happens here, right? If I put, let's say, K1 going this way, and in this case, let me take care of the external momentum too. Let's call this guy P, right? Let's call the bottom one K2. Let's include P with this guy. So I put a minus P here. That means momentum is conserved in this vertex. And you have P going out at the future. And here you have both K1 and K2. K2 is actually going the other way. So you have K1 minus K2 here, but it doesn't matter. It's still we have this propagator here that depends on both. And let's name the points, just because I'll use that soon. Right? Let's call this point X and this point W. Right? Now, in order to see what happens here, let's take first the limit of one of these two momenta going to the UV, and the other one it's still small, right? Of course, this is symmetric between the two. The asymmetry I generated here is artificial because I decided to put P there. But just for the sake of exploring, let's take K2 big and K1 small. This is equivalent of doing bringing X and W really close to each other on this side, collapsing this loop to a point without collapsing the top loop to a point, right? And we did a similar calculation to this, right? You can think of this like you have a line going into X, this point X here, right? This line is really long. The top line one can be really long because K1 is small. So I have momentum K1 minus P going in here. K1 minus P going out here, and I close the other lines here. Right? This is W. There's a line going out, right? And I have a loop with K2 here, K2 there. So this is minus K2 in that direction. I can call this vector K1 minus K2 going this way, right? And this calculation is a 4-point function, right? If I forget this upper line, I just say this K1 going out and coming in here is going through very distant from X and W. It's a very long propagator, right? Meaning this guy is, these guys are really off shell, and this guy is closer to be on shell, right? Then I know how this is. This behaves like the log, let me color this, of lambda. And I want to color this lambda green to remember that it came from K2. Right? So this is behaving like I bring these 2 points together without collapsing the only line where I don't have a really high momentum. Right? And that suggests to us, again, right? I'm not proving anything, I'm just arguing for the solution, right? That this looks a lot, this solution looks a lot like this diagram. So this is the line where I have K1 minus P flowing, right? I have momentum, external momentum P coming over here, right? But now, if I did the integration in K2, holding K1 fixed, right? I got this coefficient. Besides the Feynman rule for the vertex, I got this extra factor in front, right? That multiplies what I get from this loop. And this loop I know how to calculate. I did it before. So in green is what comes from the K2 integration. And now I do the calculation for this loop. This will look like, we know this diverges like lambda square plus the log of some lambda square, right? And now I have this P running here. So when I go to the region where K1 is not that big, right, the lower limit of the integral, this will also contribute to with a log of P square here, right? That was not here before because when you calculate this loop, there's no P running in this loop. And in this case, there is, because this is just an approximate expression for this guy in the region where K2 is bigger than K1, right? So you got this very strange expression. And I'll color everything that came from, this is the high K1 region, right? So this lambda in red comes from K1, right? So now this suggests that this kind of strange divergence, what that happens when only one of these two momenta is really high, will be concealed by the counter term going in this diagram, right? So now it's not the vertex, it's the diagram. Let me send this back so it gets clearer. So you have now the counter term here, right? Which compensates for this factor here, right? And eliminates at least part of this divergence, right? That's just a suggestion. This is very important actually, because there's something here. This is just a product of two divergences. This is just a product of two divergences. But this piece here is kind of problematic, right? So we call diagrams that have these problem, I mean, one propagator that shares momentum from both diverging loops, nested or overlapping divergences. There's actually a difference between what's nested and what's overlapping, but that's not important to us. If you're really curious, take a look at the reference I gave for Cheng and Lee, right? But these nested or overlapping divergences usually produce divergences that look like these. And this is troublesome for the very reason that if the divergence looks like that, we were kind of making mistakes in assuming that the Taylor expansion for these functions always have divergences, right? We assumed that before, that the divergence always shows as coefficients in just powers of p square, right? Just as in a polynomial of p square. This is not a polynomial of p square, this external momentum, right? This is a more complicated function, right? This, in fact, it's called a non-local divergence, right? And the ones that are proportional to just polynomials in p square are called the local divergences, right? This has to do with what kind of term you would have to put in the Lagrangian to eliminate. That's what kind of counter term, right? These are eliminated just by derivatives of the field, right? Which are local operators in your Lagrangian. This is more complicated, right? I invite you to think a little bit. What would you have to put in your Lagrangian to actually produce operator that, when translated to Feynman rules, would produce a log of p square instead of just powers of p square, which is what you get just from putting more and more derivatives on phi. Okay? Anyway, we call these divergences non-local divergence, and the thing is that they will in fact be eliminated by this counter term. I'm not showing this here, but when you add these two, right? So now what I'm saying is that this term, this thing, plus my starting diagram, let me find it. Well, I'll draw again. Easier. Too many things there. So the sum of these two guys only contain local divergences. Right? So the non-local ones are eliminated by using the counter term with this in this kind of diagram. And again, with the same conditions, with same renormalization conditions as before, because I actually demanded that something like that would be eliminated. Right? Now, there's also when the case where two of these, the two momenta go together to infinity. That brings this whole loop to a point, right? It will look something like a divergent quantity here, with both points here and all the propagators collapse to a point, right? And of course, this is easier. This is actually easier because a local divergence is eliminated by the counter term, which we already have in the Lagrangian, right? And what happens with the renormalization condition now, right? What happens with the normalization condition? Now I have more contributions to the two-point function, right? This contribution to the two-point function is now proportional to lambda square, right? I have lambda here and lambda here. So when I demand that minus im is finite, right? My delta lambda will have to equate all, will be minus all the loop contributions at a particular point in momentum, right? Now I have an extra term here. Before I only had this one. Now I have the setting sun here too. And that means that my delta lambda, which before was just, my delta lambda was just something of order lambda because it was concealing just this diagram, right? Now gets also a order lambda square contribution. So delta lambda changes, but it's still the same renormalization condition. I didn't put a new renormalization condition. I'm just seeing a power series, a perturbative series for the value of delta lambda. And the consequence of that is that with the same renormalization conditions, now I also eliminate the local divergences. This is a local term in the Lagrangian, right? And this becomes finite, right? So I didn't prove anything here, right? In fact, there is a formal proof that if your theory is, and this is very important, if your theory is renormalizable or super renormalizable, according to that superficial divergence criteria I showed before, right? Then there is a theorem that guarantees that once you put the counter terms in your Lagrangian to eliminate the divergences, the finite number of divergences that show up at a lower endpoint functions, then you eliminated everything, and this is called the BPHZ theorem, right? And that you know that by doing that counter term, the redefinition that made the counter terms appear in my Lagrangian, all the divergences at all orders in perturbation theory and for arbitrarily large endpoint functions have been eliminated, right? BPH here is Golyubov, Parasyuk, Hepp, and Zimmerman, right? And the reason, because this theorem is so important for the approach we took here, this is in many places called this whole idea of redefining the constants in terms of physical constants and then putting counter terms in the Lagrangian is called in many places the BPHZ renormalization scheme, right? In our case, we also use the on-shell scheme, and that has to do with the particular renormalization condition we use for the mass. So we demanded that the mass in the Lagrangian be the pole of the physical particles. That's also arbitrary. We could have chosen any other convenient number for the mass in the Lagrangian. Right? So I won't go much deeper into these two or more loop ideas. The important thing to remember is that there is this theorem that if you do get rid of the lower divergences, that will take care both of the subdiagrams diverging, but also of these nasty nested or overlapping divergences that I have shown, right? So that's it for this video. Thank you.